Right now, as you sit here on Earth, there is a world in our solar system that holds more liquid water than every ocean, every sea, every lake, and every river on our planet combined. And yet, this world has never seen sunlight touch its surface. It has never felt rain. It exists in the frozen darkness of deep space, more than 500 million miles from the warmth of the sun. For decades, we thought we knew the rules of the cosmos. Life needs sunlight. Oceans need warmth. Habitability means staying close to a star. But then we sent our robotic explorers out into the darkness, and they found something that changed everything. They found an ocean, not just any ocean. An ocean so vast, so deep, so incredibly ancient, that it makes our world look small by comparison. An ocean hidden beneath miles of ice, kept liquid by forces we are only beginning to understand. An ocean that might be teeming with life in forms we have never imagined. This is not science fiction. This is not speculation. This is real. And the story of how we discovered it, what it means, and what we might find when we finally dive beneath that ice, is one of the most extraordinary scientific journeys of our time. Welcome to the hidden ocean world, a place where the impossible becomes reality, a place where the search for life has only just begun. For as long as humans have looked up at the night sky, we have asked the same question: are we alone? It is a question that has haunted philosophers, inspired poets, and driven scientists to the edges of what is possible. For most of history, that question seemed impossibly difficult to answer. The universe is so vast, so unimaginably large, that even our closest stellar neighbors are trillions of miles away. But then, in the second half of the 20th century, something remarkable happened. We began to explore our own cosmic neighborhood, and what we found was far stranger and more wonderful than anyone had imagined. We discovered that the solar system is not a dead, barren place. It is alive with possibility. There are worlds with methane lakes and nitrogen rain. There are moons with active volcanoes spewing material hundreds of miles into space. There are asteroids rich with water and organic molecules, the building blocks of life itself. And then we found the ocean worlds. These are not planets like Earth. They do not orbit close to the sun. They do not have blue skies or warm beaches. Instead, they are frozen moons, locked in perpetual winter, circling the giant planets of the outer solar system. On the surface, they look dead, cold, inhospitable. But beneath that ice, hidden from view, there are oceans. Oceans that have existed for billions of years. Oceans that might be the most likely places in the entire solar system to find extraterrestrial life. In this documentary, we are going to take you on a journey to one of these worlds. We are going to show you how scientists discovered this hidden ocean, how they measured its incredible size, and how they are now planning missions to explore it. We will dive into the physics that keeps this ocean liquid, the chemistry that might make it habitable, and the biology that could be thriving in its dark, cold depths. By the end of this story, you will understand why this discovery has fundamentally changed our view of the universe. You will see why scientists now believe that life might not be rare at all, but instead could be common throughout the cosmos. hidden beneath the icy crusts of countless worlds. This is the story of the hidden ocean world. And it begins not with a telescope pointed at the stars, but with a spacecraft racing toward a tiny moon in the outer reaches of our solar system. Let us go back to the year 1979. It is a time when most people still think of the outer solar system as a frozen, lifeless wasteland. Jupiter, the largest planet in our solar system, is known to have moons, but they are thought to be simple balls of rock and ice, cold and dead, with nothing remarkable about them. Then, on March 5, 1979, a spacecraft called Voyager 1 makes its closest approach to Jupiter. It is one of the most ambitious missions in the history of space exploration, a robotic probe designed to visit the giant planets and send back the first close-up images of these distant worlds. As Voyager 1 swoops past Jupiter, its cameras turn toward the planet's moons, and what they capture will change everything. One moon in particular catches the attention of scientists. Its name is Europa. It is roughly the size of Earth's moon, about 1,900 miles in diameter, and it orbits Jupiter once every 3.5 days. But what makes Europa special is its surface. Unlike our moon, which is covered in ancient craters and dusty plains, Europa looks completely different. Its surface is smooth, incredibly smooth, with very few impact craters. Instead, it is covered in long dark streaks and ridges that crisscross the entire moon like cracks in a frozen lake. The scientists studying these images are puzzled. Why does Europa look like this? Where are all the craters? Every other rocky body in the solar system is covered in craters from billions of years of asteroid and comet impacts. But Europa looks young, geologically speaking. Something must be resurfacing this moon, erasing the old craters and creating new terrain. Then someone has an idea. What if Europa is covered in ice? Not just a thin layer of frost, but a thick shell of solid water ice. And what if, beneath that ice, there is liquid water? If that were true, then the ice shell could be constantly shifting, cracking, and reforming, driven by forces from below. That would explain the lack of craters. The surface would be young because it is constantly being renewed. At first, this idea seems almost too wild to believe. Europa is more than 480 million miles from the Sun. At that distance, temperatures are incredibly cold, far below the freezing point of water. How could there possibly be liquid water on such a frozen world? But as scientists study the images more closely, the evidence begins to pile up. The dark streaks on Europa's surface look exactly like the kind of cracks you see in sea ice on Earth. The ridges look like pressure ridges, where ice has been pushed up by forces from below. And when they analyze the color of the surface using spectroscopy, they find that it is indeed made of water ice, but not pure ice. There are other materials mixed in, including salts and organic compounds, the kind of chemicals you would expect to find if water from below had been brought to the surface. Still, they need more evidence. One spacecraft flyby is not enough to prove the existence of an ocean. So scientists start planning follow-up missions. 2 years after Voyager 1, in 1979, Voyager 2 also flies past Jupiter, and takes more images of Europa. The pictures confirm what Voyager 1 saw. Europa really does have a strange, icy surface unlike anything else in the solar system. But it will be another 16 years before we get our next close look at this mysterious moon. In 1995, NASA launches a mission called Galileo, a spacecraft designed to orbit Jupiter and study the planet and its moons in detail. Galileo arrives at Jupiter in December 1995 and begins a mission that will last for 8 years, making dozens of close flybys of Europa and the other large moons. What Galileo discovers is nothing short of astonishing. Using a magnetometer, an instrument that measures magnetic fields, scientists find that Europa has a strange magnetic signature. As Europa orbits through Jupiter's powerful magnetic field, it creates a secondary magnetic field of its own. This is called an induced magnetic field, and it can only happen if there is something electrically conductive inside Europa. On Earth, seawater is an excellent conductor of electricity because it contains dissolved salts. If Europa has a salty ocean beneath its ice, that ocean would conduct electricity and create exactly the kind of magnetic signature that Galileo is detecting. This is the smoking gun. This is the evidence that scientists have been looking for. By the time Galileo's mission ends in 2003, the case for Europa's ocean is overwhelming. Scientists estimate that beneath an ice shell about 10 to 15 miles thick, there is a global ocean of liquid water that could be 40 to 100 miles deep. To put that in perspective, the average depth of Earth's oceans is only about 2.3 miles. Europa's ocean is not just bigger than Earth's oceans. It is vastly bigger. If you added up all the water in all of Earth's oceans, seas, lakes, and rivers, Europa's ocean would contain 2 to 3 times that amount. Think about that for a moment. A moon that is smaller than our own moon, orbiting a planet more than 480 million miles from the Sun, contains more liquid water than our entire planet. It is a staggering realization, and it raises an immediate question. If Europa has an ocean, what else is out there? Are there other hidden ocean worlds in our solar system? The answer, as scientists will soon discover, is yes. There are many. But before we explore those other worlds, we need to understand how Europa's ocean can even exist. What keeps it liquid? Why hasn't it frozen solid billions of years ago? The answer lies in one of the most powerful forces in the universe. A force that stretches and squeezes Europa every single day, generating heat in the process. This force is called tidal heating, and it is the key to understanding not just Europa, but all of the ocean worlds in our solar system. To understand tidal heating, we need to start with gravity. Gravity is the force that holds the universe together. It is what keeps planets in orbit around stars, moons in orbit around planets, and you firmly planted on the ground. But gravity is not uniform. The closer you are to a massive object, the stronger the pull of gravity becomes. Now, let us think about Europa. It orbits Jupiter, the largest planet in our solar system, a gas giant with more than 300 times the mass of Earth. Jupiter's gravity is immense, and Europa feels the pull every moment of its existence. But here is the key. Europa is not a point in space. It is a moon with size and structure. The side of Europa facing Jupiter feels a stronger gravitational pull than the side facing away. This difference in gravitational pull is called a tidal force. On Earth, we see tidal forces in action every day. The moon's gravity pulls on the oceans, creating the tides we see at the beach. Water on the side of Earth facing the moon is pulled toward the moon, creating a high tide. Water on the opposite side is pulled less strongly, so it bulges outward, creating another high tide. As Earth rotates, different parts of the planet move through these bulges, and we experience rising and falling tides. But on Europa, the tidal forces are much, much stronger. Jupiter is not just bigger than Earth's moon. It is more than 20,000 times more massive. And Europa is much closer to Jupiter than our moon is to Earth. The result is that Jupiter's gravity stretches Europa by as much as 100 feet, pulling it into a slightly elongated shape. Now, if Europa were in a perfectly circular orbit, this stretching would not generate much heat. The moon would settle into a stable shape and stay that way. But Europa's orbit is not perfectly circular. It is slightly elliptical, meaning that Europa gets a little closer to Jupiter at some points in its orbit and a little farther away at others. When Europa is closer to Jupiter, the tidal forces are stronger, and the moon is stretched more. When it is farther away, the tidal forces are weaker, and the moon relaxes back toward a more spherical shape. This constant stretching and relaxing creates friction inside Europa. Just like bending a paperclip back and forth generates heat, the tidal flexing of Europa's interior generates enormous amounts of heat through friction. This heat is enough to keep the interior warm, preventing the ocean from freezing solid, despite the incredibly cold temperatures on the surface. But there is another piece to the puzzle. Why is Europa's orbit elliptical in the first place? The answer has to do with the other moons of Jupiter. Europa is not alone. It shares the space around Jupiter with dozens of other moons, including 2 other large moons called Io and Ganymede. These 3 moons are locked in what is called an orbital resonance. Here is how it works. For every one orbit that Europa makes around Jupiter, Io makes exactly 2 orbits, and Ganymede makes exactly half an orbit. This is a 4-to-2-to-1 resonance, and it is incredibly stable. The gravitational tugs from Io and Ganymede constantly pull on Europa, preventing its orbit from becoming perfectly circular. This keeps the tidal heating going, generation after generation, for billions of years. Io, the innermost of these 3 moons, experiences even more intense tidal heating than Europa. In fact, Io is the most volcanically active body in the entire solar system, with hundreds of active volcanoes constantly erupting. Europa experiences less heating than Io, but still enough to maintain a liquid ocean. Ganymede, farther out, experiences even less heating, but as we will see later, it also has an ocean of its own. So here is the picture that emerges. Europa is a small, icy moon, locked in a gravitational dance with Jupiter and its neighboring moons. This dance generates heat through tidal friction, and that heat keeps Europa's interior warm enough for liquid water to exist. The ocean is covered by a thick shell of ice, protecting it from the cold vacuum of space. And because this process has been going on for billions of years, the ocean has had an incredibly long time to evolve, to develop chemistry, and perhaps even to develop life. This is why scientists are so excited about Europa. It is not just that Europa has an ocean. It is that this ocean has all the ingredients that life needs. It has liquid water, a stable environment, and a source of energy. It also has the right chemistry. When the Galileo spacecraft analyzed Europa's surface, it found evidence of salts, sulfur compounds, and organic molecules. These are the building blocks of life as we know it. But there is something else that makes Europa even more intriguing. The ocean is not isolated. It is connected to the surface through cracks and fissures in the ice. Scientists have observed what appear to be geysers or plumes of water vapor erupting from Europa's surface, shooting material hundreds of miles into space. These plumes could be coming directly from the ocean below, which means that if there is life in that ocean, we might be able to sample it without even landing on the surface. Imagine that. A spacecraft could fly through one of these plumes, collect samples of the water vapor, and analyze them for signs of life. We could potentially detect life on Europa without ever drilling through the ice. This is one of the reasons why NASA and other space agencies are so eager to send more missions to this moon. But Europa is not the only ocean world in our solar system. Far from it. As scientists have continued to explore the outer solar system, they have found evidence of hidden oceans on several other moons. And one of those moons, a tiny world orbiting Saturn, has turned out to be even more surprising than Europa. That moon is called Enceladus, and its story begins with another historic spacecraft mission, one that would reveal secrets even more astonishing than those found at Jupiter. If Europa was a surprise, then Enceladus was a complete shock. Nobody expected what we found there. Nobody could have predicted that this tiny, frozen moon would turn out to be one of the most important discoveries in the history of planetary science. Enceladus is small, really small. It is only about 310 miles in diameter, roughly 1/7 the size of our moon, and small enough to fit inside the borders of Texas with room to spare. When scientists first observed Enceladus from Earth, they saw a faint, distant point of light. Even through powerful telescopes, it was just a tiny dot. There was no reason to think it was anything special. But in 2004, everything changed. NASA's Cassini spacecraft arrived at Saturn after a 7-year journey from Earth. Cassini was one of the most ambitious space missions ever attempted, designed to orbit Saturn for years and study the planet, its rings, and its many moons in incredible detail. One of those moons was Enceladus. On February 17, 2005, Cassini made its first close flyby of Enceladus, passing just 730 miles above the surface. The images that came back were stunning. Enceladus was covered in brilliant white ice, making it one of the brightest objects in the solar system. Its surface reflected nearly 100% of the sunlight that hit it, which meant the ice was incredibly pure and fresh. But it was not the brightness that caught scientists' attention. It was what they saw at the South Pole. There, at the bottom of the moon, were long dark streaks cutting across the ice. These were not ordinary cracks. They were enormous fractures, each one dozens of miles long and hundreds of feet deep. Scientists would later name them the tiger stripes because of their distinctive appearance. But the real mystery was not the fractures themselves. It was what was coming out of them. Cassini's instruments detected something astonishing. There was a faint haze around Enceladus, a cloud of material extending thousands of miles into space. At first, scientists were not sure what they were looking at. Was it dust? Was it gas? Then, on July 14, 2005, Cassini made another flyby, this time passing directly through the haze. The spacecraft's instruments analyzed the composition of the material, and what they found left scientists speechless. It was water. Water vapor mixed with ice crystals. Enceladus was not just a dead ball of ice. It was actively venting water into space, like a giant snow machine. These were geysers, enormous fountains of water shooting out from the fractures at the South Pole, reaching heights of more than 300 miles before falling back down or escaping into space. The discovery was so unexpected that at first, some scientists doubted it. How could a moon this small, this cold, this far from the sun be geologically active? Where was the energy coming from? But as Cassini continued to orbit Saturn, making flyby after flyby of Enceladus, the evidence became undeniable. The geysers were real, and they were spectacular. Using its instruments, Cassini was able to determine that the plumes were coming from 4 specific fractures at the South Pole, the tiger stripes. These fractures were warmer than the surrounding terrain, with temperatures reaching as high as -135 degrees Fahrenheit. That might sound cold to you, but remember, the average temperature on Enceladus's surface is -330 degrees Fahrenheit. The tiger stripes were nearly 200 degrees warmer than the rest of the moon. Something was heating them from below. The conclusion was inescapable. Beneath the icy crust of Enceladus, there had to be liquid water, and not just a little bit of water, but a substantial reservoir, possibly even a global ocean. The geysers were tapping into that ocean, bringing water from deep below the surface and launching it into space. This was a game changer. Europa had taught us that ocean worlds could exist in the outer solar system, but the evidence for Europa's ocean was indirect. We had inferred its existence from magnetic field measurements and surface features. But with Enceladus, we were seeing direct evidence. The water was right there, shooting out of the moon, and Cassini was flying through it, sampling it, analyzing it. And what Cassini found in that water was even more exciting than the discovery of the plumes themselves. When scientists analyzed the composition of the plume material, they found that it was not just water. It was a complex mixture of different chemicals. There was water vapor, of course, but also salt, silica particles, carbon dioxide, methane, ammonia, and a variety of organic molecules. Organic molecules are compounds that contain carbon and hydrogen, and they are the building blocks of life as we know it. The presence of these chemicals told scientists several important things. First, the water in Enceladus's ocean is salty, just like Earth's oceans. Second, the ocean is in contact with a rocky core, because the silica particles could only have formed through interactions between hot water and rock. Third, There are chemical reactions happening in that ocean, reactions that are producing methane and other organic compounds. On Earth, we know of places where similar chemistry occurs. At the bottom of our oceans, there are hydrothermal vents, cracks in the seafloor where hot water rich in minerals and chemicals flows out into the cold seawater. These vents are oases of life in the deep ocean. Even though sunlight never reaches these depths and photosynthesis is impossible, life thrives there. Microbes feed on the chemicals coming out of the vents, and larger organisms feed on the microbes. These ecosystems do not need sunlight. They are powered entirely by chemistry. Could the same thing be happening on Enceladus? Could there be hydrothermal vents at the bottom of its ocean, creating the same kind of chemistry and perhaps even the same kind of life? It is not just possible, it is likely. In 2017, scientists announced another stunning discovery. They had detected molecular hydrogen in Enceladus's plumes. Hydrogen is not just an organic molecule. It is a potential source of chemical energy for life. On Earth, there are microbes called methanogens that consume hydrogen and carbon dioxide and produce methane as a waste product. These microbes are some of the simplest forms of life on our planet, and they can survive in incredibly harsh environments. The discovery of hydrogen in Enceladus's plumes means that all the necessary ingredients for this kind of life are present. There is liquid water. There is chemical energy in the form of hydrogen. There are carbon compounds. There is a rocky seafloor where chemistry is happening. Everything you need for life is there. Now, let us be clear. Detecting the ingredients for life is not the same as detecting life itself, but it means that Enceladus is a habitable environment. It has the potential to support life. And because the plumes are constantly bringing material from the ocean to the surface, we have a unique opportunity to study that ocean without ever landing on the moon. Imagine this. A future spacecraft could orbit Enceladus and fly through the plumes repeatedly, collecting samples and analyzing them for biosignatures, signs of life. It could look for amino acids, the building blocks of proteins. It could search for complex organic molecules that might be produced by living organisms. It could even look for the microbes themselves. This is not science fiction. This is a real mission that scientists are planning right now. NASA is developing a mission called the Enceladus Orbilander, which would do exactly what I just described. It would orbit Enceladus, fly through the plumes, collect samples, and then eventually land on the surface to study the ice and search for signs of life. But Enceladus has given us more than just the possibility of finding life. It has also taught us something profound about the solar system. It has shown us that even the smallest, most unlikely worlds can harbor oceans and a potential for life. Before Enceladus, most scientists thought that habitability was limited to the habitable zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Earth is in the habitable zone of the Sun. Mars is at the edge of it. But Europa and Enceladus are nowhere near the habitable zone. They are in the frozen outer solar system where the sun is weak and distant. Yet they have oceans. And if these tiny moons can have oceans, then so can countless other moons and worlds throughout the galaxy. The universe might be teeming with ocean worlds, hidden beneath icy crusts, each one a potential home for life. But how common are these worlds? How many of them are out there? To answer that question, we need to look at the other giant planets in our solar system and see what other secrets they are hiding. Europa and Enceladus are the stars of the ocean world story, but they are not alone. As scientists have continued to study the outer solar system, they have found evidence of hidden oceans on several other moons. And each one of these discoveries has deepened our understanding of how common liquid water might be in the universe. Let us start with Ganymede, the largest moon in our solar system. Ganymede is bigger than the planet Mercury, with a diameter of 3,270 miles. It orbits Jupiter just beyond Europa, and for a long time, scientists thought it was simply a large ball of rock and ice, cold and geologically dead. But in 2015, using the Hubble Space Telescope, scientists made a surprising discovery. They were studying Ganymede's auroras, glowing ribbons of light similar to the northern lights on Earth. These auroras are created when charged particles from Jupiter's magnetosphere strike Ganymede's thin atmosphere. But the Hubble observations showed something strange. The auroras were wobbling in a very specific way, and the only explanation for this wobbling was that Ganymede has a subsurface ocean of salty water. Here is how it works. Ganymede, like Europa, creates an induced magnetic field as it orbits through Jupiter's powerful magnetic field. But if there is a salty ocean beneath the surface, that ocean acts as an electrical conductor, and it influences the way the magnetic field interacts with Ganymede's auroras. The wobbling of the auroras was the clue that revealed the ocean's presence. Scientists now believe that Ganymede's ocean is about 60 miles beneath the surface, buried under several layers of ice and possibly even high-pressure forms of ice that do not exist on Earth. Ocean itself could be as much as 60 miles deep, making it one of the largest oceans in the solar system. In fact, Ganymede might contain more water than Europa. If that is true, then Ganymede has more liquid water than all of Earth's oceans combined, just like Europa. But Ganymede's ocean is different from Europa's in one important way. It is much deeper beneath the surface, which makes it harder to study and harder to access. The thick layers of ice above the ocean mean that plumes, like those on Enceladus, are unlikely. And the depth means that any future mission to Ganymede would need to drill much deeper to reach the ocean. Still, the discovery is significant because it shows that even moons farther from Jupiter, where tidal heating is weaker, can still maintain liquid oceans. Then there is Callisto, the outermost of Jupiter's 4 large moons. Callisto is ancient and heavily cratered, one of the oldest surfaces in the solar system. For years, scientists thought it was geologically dead, with no activity whatsoever. But magnetic field measurements from the Galileo spacecraft suggested that Callisto, too, might have a subsurface ocean, buried perhaps 60 to 100 miles beneath the surface. If Callisto has an ocean, it is probably very cold, very salty, and sandwiched between layers of ice. It is not as promising a target for the search for life as Europa or Enceladus, but it is still an ocean world. Now let us leave Jupiter and travel farther out to Saturn. We have already talked about Enceladus, But Saturn has another moon that might have a hidden ocean. Its name is Titan, and it is one of the most fascinating places in the entire solar system. Titan is the second largest moon in the solar system, only slightly smaller than Ganymede. But unlike any other moon, Titan has a thick atmosphere, even thicker than Earth's. This atmosphere is made mostly of nitrogen, with clouds of methane and ethane. The surface of Titan is hidden beneath this thick haze, and for years, nobody knew what was down there. Then, in 2005, the Cassini spacecraft released a small probe called Huygens, which descended through Titan's atmosphere and landed on the surface. The images it sent back were astonishing. Titan has rivers, lakes, and seas, but they are not made of water. They are made of liquid methane and ethane. It rains on Titan, but instead of water, it rains hydrocarbons. Titan is a bizarre, alien world, unlike anything else we have ever seen. But beneath the surface, hidden under a crust of water ice, Titan might have something even more remarkable. Gravitational measurements from Cassini suggest that Titan has a subsurface ocean of liquid water, possibly mixed with ammonia. This ocean could be 30 to 60 miles beneath the surface, making it difficult to access, but it is still there. What makes Titan especially interesting is that it has two kinds of liquid environments. On the surface, you have lakes and seas of liquid methane and ethane, which is a completely different kind of chemistry from anything on Earth. And beneath the surface, you have a water ocean, where the chemistry might be more familiar. Some scientists have speculated that Titan could potentially host two different kinds of life, one adapted to the hydrocarbon lakes on the surface, and another living in the water ocean below. It sounds like science fiction, but it is a real possibility that scientists are seriously considering. Now let us go even farther out, beyond Saturn, to the ice giants, Uranus and Neptune. These planets are so distant and so cold that until recently, most scientists assumed their moons would be lifeless balls of ice. But we are starting to learn that even here, in the frozen darkness of the outer solar system, ocean worlds might exist. One of the most intriguing candidates is Triton, Neptune's largest moon. Triton is unusual for several reasons. First, it orbits Neptune in the opposite direction from the planet's rotation, which suggests that it was captured by Neptune's gravity rather than forming alongside the planet. Second, Triton has geysers, similar to those on Enceladus. These geysers erupt nitrogen gas and dark organic material, creating long streaks across the surface. When Voyager 2 flew past Triton in 1989, it observed these geysers and found that Triton is geologically active. This suggests that there is heat inside Triton, and where there is heat, there could be liquid water. Some scientists believe that Triton might have a subsurface ocean, kept liquid by tidal heating as Neptune's gravity flexes the moon's interior. If true, Triton would be the most distant ocean world we have discovered so far. There is also speculation that Uranus's moon, Miranda, might have an ocean. Miranda is small, only about 290 miles in diameter, but its surface is incredibly strange. It looks like it has been torn apart and reassembled, with cliffs, canyons, and ridges unlike anything else in the solar system. So scientists think this chaotic terrain could be the result of tidal heating and cryovolcanism, the eruption of water and ice from the interior. If Miranda has an ocean, it would be another example of how even the smallest moons can harbor hidden seas. So let us take stock. In our solar system alone, we have found evidence of oceans on at least 6 worlds: Europa, Ganymede, Callisto, Enceladus, Titan, and possibly Triton and Miranda. That is more ocean worlds in our solar system than there are rocky planets. Think about that. For most of human history, we thought Earth was the only world with oceans. Now we know that ocean worlds are common, perhaps even the norm, in the outer solar system. And here is the truly mind-blowing part. If our solar system has this many ocean worlds, how many must there be in the entire galaxy? There are hundreds of billions of stars in the Milky Way, and many of those stars have planets and moons. If even a small fraction of those moons are ocean worlds, then the galaxy could contain trillions of hidden oceans, trillions of potential homes for life. This realization has fundamentally changed the way scientists think about the search for life in the universe. For decades, the search focused on finding planets in the habitable zone, the region around a star where liquid water can exist on the surface. But now we know that habitability is not limited to the habitable zone. Ocean worlds can exist anywhere, as long as there is a source of heat to keep the water liquid. And that heat does not have to come from a star. It can come from tidal forces, from radioactive decay in the moon's core, or from chemical reactions in the interior. This means that the potential for life in the universe is far greater than we ever imagined. Life does not need a warm, sunny planet with a breathable atmosphere. It can exist in the dark, beneath miles of ice, in oceans kept liquid by the gravity of giant planets. And if life can exist in these places, then the universe might be teeming with it, hidden from view, waiting to be discovered. But to find that life, we need to understand these ocean worlds better. We need to know how deep the oceans are, what the chemistry is like, whether there are hydrothermal vents, and whether the conditions are right for life to emerge. And to answer those questions, we need to send more missions to these moons. We need to land on them, drill through the ice, and explore the oceans directly. That is the next chapter of this story. The missions we are planning, the technology we are developing, and the incredible challenges we face as we prepare to explore the hidden oceans of the outer solar system. So far, we have talked about the discovery of these hidden ocean worlds and the tantalizing evidence that they might be habitable. But there is a question that we need to address. How do we know these oceans are really there? After all, we cannot see them. They are buried beneath miles of ice on worlds that are hundreds of millions of miles away. What evidence do scientists have that these oceans actually exist? And how can they be so sure about their size and depth? The answer lies in some of the most ingenious detective work in the history of science. Scientists have developed multiple methods to detect and study these hidden oceans, using everything from magnetic fields to gravity measurements to computer models. Each method provides a different piece of the puzzle, and when you put them all together, the picture becomes clear. Let us start with magnetic fields. because this was one of the first methods used to detect Europa's ocean. Every planet and moon has a magnetic field, or at least every object with a liquid, electrically conductive interior. Earth's magnetic field is generated by the movement of molten iron in the planet's outer core. This is called a dynamo, and it creates a strong, stable magnetic field that has existed for billions of years. But Europa does not have a dynamo. Its core is probably solid, or at least not large enough to generate a dynamo like Earth's. So when the Galileo spacecraft measured Europa's magnetic field, scientists expected to find nothing, or perhaps just a weak, static field. Instead, they found something very unusual. Europa's magnetic field was changing over time, flipping direction as the moon orbited Jupiter. This was a clear sign of an induced magnetic field. Here is how it works. Jupiter has an incredibly strong magnetic field, one of the strongest in the solar system. As Europa orbits through this field, the magnetic field lines pass through the moon, and if there is something electrically conductive inside Europa, it will create electric currents. Those currents, in turn, generate their own magnetic field, which we can detect from space. On Earth, seawater is a good conductor of electricity because it contains dissolved salts. Fresh water is a poor conductor, but salty water conducts electricity very well. So if Europa has a salty ocean beneath its ice, that ocean would create exactly the kind of induced magnetic field that Galileo detected. The strength and pattern of the field tell us how deep the ocean is and how salty it is. Using this method, scientists estimated that Europa's ocean is about 40 to 100 miles deep, and that it is at least as salty as Earth's oceans, possibly much saltier. This was the first strong evidence that Europa really does have a global ocean of liquid water. The same method has been used to detect oceans on Ganymede and Callisto. In both cases, the moons show induced magnetic fields, which means they have electrically conductive layers beneath the surface. For Ganymede, the evidence is particularly strong because the Hubble Space Telescope was able to observe the wobbling of the moon's auroras, which is directly caused by the interaction between the magnetic field and the subsurface ocean. But magnetic fields are not the only way to detect hidden oceans. Another powerful method is to measure the moon's gravity, and specifically, how that gravity changes as the moon orbits its parent planet. This technique is called gravimetry, and it works by tracking the trajectory of a spacecraft as it flies past a moon. As the spacecraft approaches the moon's gravity pulls on it, causing the spacecraft to speed up slightly. As the spacecraft moves away, the gravity weakens and the spacecraft slows down. By measuring these tiny changes in speed, scientists can create a detailed map of the moon's gravitational field. Now, here is the key. The strength of gravity at any given point depends on the distribution of mass inside the moon. If a moon has a dense, rocky core, the gravity will be stronger in certain areas. If it has a liquid ocean, the gravity will be different because liquids are less dense than rock. By studying the pattern of gravity, scientists can figure out the internal structure of the moon, even though they cannot see inside it. Cassini used this method to study Enceladus. By making dozens of flybys and carefully measuring the tiny changes in the spacecraft's velocity, Scientists were able to determine that there is a large reservoir of liquid water beneath the south pole of Enceladus. The gravity data showed that the water is probably regional, concentrated beneath the tiger stripes, but it could also be part of a global ocean that is thicker at the South Pole. Gravimetry has also been used to study Titan. By tracking Cassini's trajectory as it flew past Titan dozens of times, scientists discovered that Titan's gravitational field changes slightly depending on where the moon is in its orbit. This change is consistent with a subsurface ocean that sloshes back and forth as Titan orbits Saturn. If the interior were solid, this sloshing would not happen. But if there is a liquid ocean, the gravity signature makes perfect sense. Another method scientists use is called libration analysis. Libration is a slight wobble in the way a moon rotates. Most moons, including our own moon, are tidally locked, which means they always show the same face to the planet they orbit. But even though they are locked, they can still wobble slightly as they move through their orbits. If a moon has a solid interior, the wobble will be very small. But if there is a liquid ocean beneath the surface, the icy crust can move independently from the interior, and the wobble will be larger. By measuring the libration of a moon, scientists can determine whether there is a liquid layer inside. This method was used to confirm Europa's ocean. By carefully tracking the position of surface features over time, scientists measured the libration of Europa's icy shell and found that it was wobbling more than expected. This could only happen if the ice shell is floating on top of a liquid ocean, decoupled from the rocky interior below. The same technique has been used to study Enceladus and Titan. In both cases, the libration data support the hypothesis of a subsurface ocean. These wobbles are tiny, often just a few meters, but with modern instruments, we can measure them with incredible precision. So we have magnetic fields, gravity measurements, and libration analysis. But there is one more method that scientists use, and it is perhaps the most direct of all. That method is spectroscopy, the study of light and how it interacts with matter. When sunlight hits the surface of a moon, some of that light is reflected back into space, and some is absorbed. The pattern of reflection and absorption depends on the materials on the surface. Ice reflects light differently than rock. Salt reflects light differently than organic compounds. By analyzing the spectrum of light coming from a moon, scientists can determine what the surface is made of. On Europa, spectroscopy has revealed the presence of water ice as expected, but also salts like sodium chloride and magnesium sulfate, as well as sulfur compounds and organic molecules. These materials are not uniformly distributed. They are concentrated in the cracks and ridges on the surface, which suggests that they have been brought up from below, possibly by the eruption of liquid water or briny slush. On Enceladus, spectroscopy has been even more revealing. When Cassini flew through the plumes, it did not just detect water vapor. It detected a whole range of chemicals, including salt, silica, carbon dioxide, methane, ammonia, and complex organic molecules. By studying the exact composition of these materials, scientists have been able to learn about the chemistry of the ocean without ever touching it. For example, the presence of silica particles tells us that the ocean is in contact with a rocky core, and that the water is warm enough to dissolve silica from the rock. On Earth, silica dissolves in water at temperatures above 200 degrees Fahrenheit, so the ocean beneath Enceladus is not ice cold. It is warm, at least in some regions, probably near hydrothermal vents on the seafloor. The presence of molecular hydrogen is even more significant. Hydrogen is produced when hot water reacts with certain kinds of rock in a process called serpentinization. This is the same process that occurs at hydrothermal vents on Earth, and it provides chemical energy that microbes can use to survive. The detection of hydrogen in Enceladus's plumes is one of the strongest pieces of evidence that the moon could support life. Finally, there is one more technique that scientists use to study these ocean worlds, and that is computer modeling. Using powerful supercomputers, scientists can simulate the interiors of these moons, taking into account everything we know about their size, mass, composition, and orbital dynamics. These models allow scientists to test different hypotheses and see which ones best match the observations. For example, scientists have used models to determine how thick Europa's ice shell is likely to be, how much heat is generated by tidal flexing, and how the ocean might circulate. They have found that the ice shell is probably between 10 and 15 miles thick, and that the ocean below is at least 40 miles deep. They have also found that the ocean is probably stratified, with warmer, less salty water near the top and colder, saltier water near the bottom. Computer models have also been used to study Enceladus. Scientists have simulated the plumes, trying to understand how water can be launched hundreds of miles into space. They have found that the plumes are probably driven by a combination of vapor pressure and tidal pumping. As Enceladus orbits Saturn, the tidal forces open and close the fractures at the South Pole, creating a pumping action that forces water out of the ocean and into space. These models are incredibly sophisticated, and they are constantly being refined as we gather more data. But they are essential tools for understanding these hidden oceans, because they allow us to see inside the moons in ways that direct observation cannot. So when you put all of these methods together, magnetic fields, gravity measurements, libration analysis, spectroscopy, and computer modeling, you get a detailed picture of what these ocean worlds are like. And that picture is remarkable. We know that Europa has a global ocean of salty water, at least 40 miles deep, beneath an ice shell 10 to 15 miles thick. We know that the ocean is in contact with a rocky seafloor, and that there is chemistry happening at the boundary between the water and the rock. We know that material from the ocean is being brought to the surface through cracks and possibly plumes. We know that Enceladus has a subsurface ocean, at least at the South Pole, that is warm enough to dissolve silica and produce molecular hydrogen. We know that the ocean is connected to the surface through the tiger stripes, and that plumes are constantly bringing ocean material into space, where we can sample it. We know that Ganymede, Callisto, Titan, and possibly other moons also have subsurface oceans, each with their own unique characteristics and chemistry. And we know that these oceans are not just small pockets of water. They are vast, deep, ancient bodies of liquid that have existed for billions of years. This is not speculation. This is solid science, based on multiple lines of evidence from multiple missions. The hidden ocean worlds are real, and they are waiting to be explored. But there is one more question we need to ask. If these oceans are so large and so ancient, what are the chances that they harbor life? To answer that question, we need to understand what life needs to survive, and whether these ocean worlds can provide those conditions. Before we dive into the question of life, let us take a moment to pause and think about what these ocean worlds are really like. Not just the science, but the experience. What would it be like to stand on the surface of Europa or Enceladus? What would you see? What would you hear? Close your eyes for a moment and imagine this. You are standing on the surface of Europa. Above you, the sky is black, not the blue of Earth's sky, but the absolute black of space. There is no atmosphere here, no air to scatter the sunlight. The stars are sharp points of light, unblinking, and among them, one star shines brighter than all the rest. That is the sun, 480 million miles away. A distant, cold point of light that provides only a fraction of the warmth and brightness it gives to Earth. But there is something else in the sky, something enormous and overwhelming. Jupiter, the giant planet, hangs in the sky, filling a huge portion of the horizon. It is more than 11 times the diameter of Earth, and from Europa's surface, it looks impossibly large. A swirling sphere of orange and brown clouds, with the great red spot, a storm larger than Earth itself, slowly rotating across the face of the planet. Jupiter does not move across the sky like the moon does on Earth. Because Europa is tidally locked, Jupiter stays in the same position, always hanging above the same spot on the horizon. If you stand on the hemisphere facing Jupiter, you will see the giant planet all the time. If you stand on the opposite side, you will never see it. The surface beneath your feet is ice, water ice, as hard as rock in the intense cold. The temperature here is about minus 260 degrees Fahrenheit, cold enough to freeze carbon dioxide, cold enough to turn nitrogen into liquid. The ice is not smooth. It is covered in ridges, cracks, and chaos terrain, regions where the surface has been fractured and jumbled by forces from below. You walk carefully across the surface, and with each step, your boots crunch into the ice. There is no wind here, no weather, no erosion. Every footprint you make will last for millions of years, preserved in the frozen surface until some future geological event erases it. But as you walk, you begin to notice something. The ice beneath your feet is not silent. You can feel vibrations, subtle tremors, as the moon flexes and shifts in response to Jupiter's gravity. And if you listen carefully, very carefully, you might hear something else. A deep, distant creaking, the sound of ice moving, cracking, adjusting to the tidal forces that stretch and compress it every few days. Somewhere beneath your feet, miles below, there is an ocean. You cannot see it, you cannot hear it directly, but you know it is there. And in that ocean, there might be life. Strange, alien life, adapted to the darkness and the cold, thriving in an environment that no human has ever seen. That is Europa, a world of ice and mystery, a world where the impossible is real. Now, imagine Enceladus. The gravity here is much weaker, only about 1% of Earth's gravity. So every step you take launches you gently into the air. The surface is even brighter than Europa's, so bright that the glare is almost painful. The ice here is pure, untouched by the radiation and dust that discolor other moons. But the most astonishing thing about Enceladus is the geysers. At the South Pole, enormous fountains of water vapor and ice crystals are erupting from the tiger stripes, shooting hundreds of miles into space. If you stand near one of these plumes, you can see it rising above the horizon, a column of mist and ice glittering in the sunlight, backlit by the distant sun. And if you listen, you might hear something extraordinary. The ice is alive with sound. The cracks and fractures are constantly opening and closing as Enceladus orbits Saturn, and with each tidal cycle, water and vapor rush through the fissures, creating a hissing, roaring sound like the breath of the moon itself. This is a world in motion, a world that is geologically active, a world that is constantly changing. And beneath the ice, there is an ocean, warm and salty and full of chemistry. An ocean that might be one of the best places in the entire solar system to search for life. These are not dead worlds. They are alive in their own way, shaped by forces that we are only beginning to understand. And the more we learn about them, the more we realize how little we know. Now we come to the question that drives this entire story. Can these hidden oceans support life? Not just in theory, but in practice? What are the conditions like in these oceans? And do they match the requirements for life as we know it? To answer this question, we need to start with the basics. What does life need? If you ask a biologist, they will give you a list of essential ingredients. Life needs liquid water. It needs a source of energy. It needs raw materials, the chemical building blocks like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And it needs time, lots of time, for evolution to do its work. Let us take these one at a time and see how the ocean worlds measure up. First, liquid water. This is the most fundamental requirement. Water is the universal solvent, the medium in which biochemical reactions occur. Every form of life on Earth, from bacteria to blue whales, depends on water. Without it, life as we know it cannot exist. The ocean worlds pass this test with flying colors. Europa, Enceladus, Ganymede, Titan, and possibly others all have liquid water beneath their surfaces. These are not tiny pockets of water. They are vast oceans, some of them deeper than Earth's oceans, with volumes measured in the millions of cubic miles. Second, energy. Life needs energy to grow, reproduce, and maintain itself. On Earth, most life gets its energy from the sun through photosynthesis. Plants capture sunlight and convert it into chemical energy, and animals eat the plants or each other. But photosynthesis only works if there is sunlight, and in the oceans of the outer solar system, there is no sunlight. The oceans are buried beneath miles of ice, completely dark, completely isolated from the sun. But that does not mean there is no energy. On Earth, there are ecosystems that do not depend on sunlight. At the bottom of the ocean, at hydrothermal vents, life thrives in complete darkness. These ecosystems are powered by chemosynthesis, a process where microbes extract energy from chemical reactions rather than from sunlight. Hydrothermal vents form where seawater seeps into cracks in the ocean floor, gets heated by magma below, and then erupts back into the ocean, carrying dissolved minerals and gases. The hot water is rich in chemicals like hydrogen sulfide, methane, and hydrogen, and microbes have evolved to use these chemicals as a source of energy. These microbes form the base of the food chain, and larger organisms like tube worms and clams depend on them for survival. Could the same thing be happening in the oceans of Europa or Enceladus? The evidence suggests yes. On Enceladus, the detection of molecular hydrogen in the plumes is a strong indication that hydrothermal activity is occurring at the bottom of the ocean. Hydrogen is produced when hot water reacts with certain types of rock, particularly olivine, a common mineral in rocky bodies. This reaction, called serpentinization, not only produces hydrogen, but also releases heat and creates alkaline conditions that are favorable for life. On Earth, serpentinization occurs at a type of hydrothermal vent called a lost city vent. These vents are different from the more famous black smokers. They are cooler, more alkaline, and produce a steady flow of hydrogen and methane. Some scientists believe that life on Earth might have originated at lost city-style vents because the chemistry is so favorable for the formation of organic molecules. If Enceladus has similar vents, then it has a ready-made source of chemical energy and potentially a cradle for life. Europa is also a good candidate for hydrothermal activity. The tidal heating that keeps Europa's ocean liquid also heats the rocky core, and where hot rock meets water, chemistry happens. Scientists have not detected hydrogen in Europa's plumes yet, but that is only because we have not sampled the plumes as thoroughly as we did on Enceladus. Future missions might find the same chemical signatures, so we have water and we have energy. What about raw materials? Life on Earth is based on 6 main elements, often remembered by the acronym CNOPS: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements are the building blocks of proteins, DNA, cell membranes, and all the other molecules that make up living organisms. The good news is that these elements are abundant in the universe. Carbon is one of the most common elements in the cosmos, created in the cores of stars. Hydrogen is the most abundant element of all, left over from the Big Bang. Nitrogen, oxygen, phosphorus, and sulfur are also relatively common, produced in supernova and scattered throughout the galaxy. In the oceans of the outer solar system, we have already detected many of these elements. On Enceladus, the plumes contain water, hydrogen and oxygen, carbon dioxide, carbon and oxygen, methane, carbon and hydrogen, ammonia, nitrogen and hydrogen, and various organic molecules that contain carbon, hydrogen, nitrogen, and oxygen. The presence of salts and silica particles suggests that there are also minerals and potentially phosphorus and sulfur in the ocean. On Europa, spectroscopy has revealed water ice, salts, sulfur compounds, and organic molecules on the surface. These materials have likely been brought up from the ocean below, which means the ocean contains at least some of the building blocks of life. Now, Detecting the building blocks is not the same as detecting life itself, but it is a necessary first step. If the ocean did not contain these elements, life would be impossible. The fact that they are present means that the chemistry is right for life to emerge if the conditions are favorable. So we have water, energy, and raw materials. What about time? This is where the ocean worlds really shine. These oceans are ancient. Europa's ocean has likely existed for billions of years, possibly since the moon formed 4.5 billion years ago. Enceladus's ocean might be younger, but it is still probably hundreds of millions of years old, possibly longer. Ganymede and Titan's oceans are also billions of years old. On Earth, life emerged relatively quickly. The planet formed about 4.5 billion years ago, and the earliest evidence of life dates back to about 3.8 billion years ago, possibly even earlier. That means life appeared within the first few 100 million years of Earth's history, as soon as the planet cooled down enough to have liquid water and stable conditions. If life can emerge that quickly on Earth, then it is entirely possible that it has also emerged on Europa, Enceladus, or other ocean worlds. They have had billions of years for chemistry to become biology, for simple organic molecules to organize themselves into something more complex, for evolution to take hold. But there is one more thing life needs, and it is perhaps the most important of all. Life needs stability. It needs an environment that does not change too dramatically over time. If the ocean freezes solid, and then melts, and then freezes again, life would have a hard time getting started. But if the ocean remains liquid for billions of years, with a stable temperature and chemistry, then life has a chance to evolve and diversify. The ocean worlds seem to provide that stability. The tidal heating that keeps the oceans liquid is a continuous process, driven by the gravitational interactions between the moons and their parent planets. As long as those moons remain in their current orbits, the heating will continue and the oceans will remain liquid. There is no reason to think this will change anytime soon. Jupiter has been where it is for billions of years, and so have its moons. The same is true for Saturn and its moons. So when we look at the ocean worlds through the lens of biology, we see environments that have everything life needs. They have liquid water in abundance. They have chemical energy from hydrothermal activity. They have the raw materials for building cells and molecules. And they have had billions of years of stable conditions for life to emerge and evolve. But there is still a big question. Just because an environment can support life does not mean that life is actually there. Life might be common in the universe, or it might be incredibly rare. We do not know yet. The only way to find out is to go there and look. And that brings us to the next part of the story. What kind of life might we find in these hidden oceans, if it exists at all? What would it look like? How would it survive in such extreme conditions? And how would we detect it? These are the questions that scientists are grappling with right now, and the answers will shape the future of astrobiology in the search for life beyond Earth. Let us take a moment to imagine something. Imagine you are on a spacecraft descending toward Europa. You have landed on the icy surface, and your mission is to drill through the ice shell and reach the ocean below. After weeks of drilling, you finally break through. Your drill withdraws, and a small robotic submarine descends into the darkness. At first, there is nothing, just blackness and cold. The submarine's lights pierce the water, but they reveal very little. The water is clear, cleaner than anything on Earth, because there is no sunlight, no photosynthesis, and therefore no algae or plankton to cloud it. The submarine descends deeper and deeper, passing through the cold upper layers of the ocean, heading toward the seafloor miles below. And then you see it, a faint glow in the distance. As you approach, the glow becomes brighter, and you realize it is coming from a hydrothermal vent, a crack in the seafloor where hot water is pouring out into the cold ocean. The water around the vent is warm, perhaps 200 or 300 degrees Fahrenheit, and it is rich in dissolved minerals and chemicals. And there, clinging to the rocks around the vent, are structures. Not rocks, not minerals, but something else. Something alive. This is the dream of astrobiologists. This is what we hope to find when we finally explore the oceans of Europa or Enceladus. But what would that life actually look like? Would it resemble anything on Earth? Or would it be something completely alien, something beyond our imagination? To answer that question, we need to think about what life is at its most fundamental level. Life is a chemical process, a system that can take in energy and raw materials, use them to build and maintain itself, and reproduce. On Earth, all life is based on carbon chemistry, with DNA as the genetic material and proteins as the molecular machines that do the work. But is this the only way life can be? Most scientists think that life elsewhere in the universe will also be carbon-based, because carbon is uniquely suited for building complex molecules. Carbon atoms can form 4 chemical bonds, which allows them to link together in long chains and complex structures. No other element has quite the same versatility. Silicon, which is chemically similar to carbon, can also form complex molecules, but silicon-based life would face serious challenges, especially in a water-based environment. So if we find life in the oceans of Europa or Enceladus, it will probably be carbon-based, and it will probably use water as a solvent, just like life on Earth. But beyond that, it could be very different. Let us start with the simplest possibility: single-celled microbes, similar to bacteria or archaea on Earth. These are the kinds of organisms that thrive at Earth's hydrothermal vents, and they are probably the most likely form of life we will find on ocean worlds. These microbes would be chemotrophs, organisms that get their energy from chemical reactions rather than from sunlight. They would live near hydrothermal vents, where they could access the hydrogen, methane, and other chemicals they need to survive. They would be small, probably just a few micrometers in size, and they would reproduce by simple cell division. On Earth, chemotrophic microbes are incredibly diverse. Some of them are methanogens, organisms that consume hydrogen and carbon dioxide and produce methane. Others are sulfur bacteria, which oxidize hydrogen sulfide and produce sulfur. Still others are iron bacteria, which extract energy from the oxidation of iron. All of these kinds of organisms could potentially exist in the oceans of Europa or Enceladus, adapted to the specific chemistry of those environments. But could life on these ocean worlds evolve beyond single cells? Could there be multicellular organisms, things that we might recognize as animals or plants? On Earth, the evolution of multicellular life took a long time. Single-celled organisms appeared about 3.8 billion years ago, but multicellular life did not emerge until about 600 million years ago, during a period called the Ediacaran. That is more than 3 billion years of single-celled life before anything more complex appeared. Why did it take so long? The answer is oxygen. Most multicellular life on Earth depends on aerobic respiration, a process that uses oxygen to extract energy from food. Oxygen is incredibly efficient, providing much more energy than anaerobic processes like fermentation. But for most of Earth's history, there was very little oxygen in the atmosphere. It was only after photosynthetic bacteria began producing oxygen, and after that oxygen built up over millions of years, that multicellular life could evolve. In the oceans of Europa or Enceladus, there is probably no oxygen, or at least very little of it. Without oxygen, it is hard for complex, energy-intensive organisms to evolve. So the most likely scenario is that life in these oceans, if it exists, is still at the microbial stage. But that does not mean it is simple or boring. Microbial life can form incredibly complex ecosystems. On Earth, microbial mats, biofilms, and stromatolites are examples of how microbes can organize themselves into structures that resemble multicellular organisms. These structures can be quite large, and they can create their own microenvironments, altering the chemistry of the water around them to make it more favorable for their survival. We might find similar structures around the hydrothermal vents of Europa or Enceladus. Imagine vast fields of microbial mats covering the seafloor around a vent, metabolizing the chemicals in the hot water and slowly building up layers of mineral deposits. These structures could be ancient, growing for millions of years, creating a record of the ocean's history in the minerals they leave behind. There is also another possibility, one that is more speculative, but still worth considering. What if the oceans of these worlds have evolved life that uses a completely different energy source, something we have not thought of? On Earth, there is a type of microbe called a radiotrophic fungus that can use radiation as an energy source. These fungi contain a pigment called melanin, which can absorb gamma rays and use them to drive chemical reactions, in a process somewhat similar to photosynthesis, but using radiation instead of light. These fungi were discovered in the ruins of the Chernobyl nuclear reactor, where radiation levels are extremely high. Could something similar exist on Europa? The surface of Europa is constantly bombarded by high-energy radiation from Jupiter's magnetosphere. This radiation breaks apart water molecules on the surface, creating hydrogen peroxide, oxygen, and other reactive chemicals. Some of these chemicals could make their way down through cracks in the ice and into the ocean. If life in the ocean could tap into these chemicals as a source of energy, it would have access to an energy source that is completely independent of hydrothermal vents. This is highly speculative, and we have no evidence that such a process is actually happening. but it is an example of how life might adapt to the unique conditions of an alien ocean, using resources and strategies that we have never seen on Earth. Now, let us think about another possibility. What if life in these oceans has evolved senses and behaviors that are completely alien to us? On Earth, most animals rely on vision, hearing, smell, and touch to navigate their environment. But in the deep oceans of Europa or Enceladus, vision would be useless. There is no sunlight, and even if organisms produced bioluminescence, as many deep-sea creatures on Earth do, the range of vision would be very limited. Instead, life in these oceans might rely on other senses. They might use chemoreception, detecting gradients of chemicals in the water to find food and navigate toward hydrothermal vents. They might use mechanoreception, sensing vibrations and pressure changes in the water caused by other organisms or by geological activity. They might even use electroreception, detecting the faint electrical fields generated by living organisms, similar to how sharks and rays on Earth can sense the electrical activity of their prey. If complex organisms did evolve in these oceans, they might be completely alien in appearance and behavior. They might move slowly, conserving energy in the cold, dark water. They might have no eyes, no limbs as we know them, but instead tentacles or cilia for sensing and manipulating their environment. They might communicate through chemical signals or vibrations, rather than sound or light. This is pure speculation, of course, but it is speculation grounded in what we know about how life adapts to extreme environments on Earth. Life is incredibly resourceful. It finds a way to survive and thrive in the most unlikely places, from the boiling hot springs of Yellowstone to the acidic lakes of volcanic craters to the frozen deserts of Antarctica. If life can exist in those places on Earth, why not in the hidden oceans of the outer solar system? But here's the challenge. Even if life exists in these oceans, how would we detect it? This is not like searching for life on Mars, where we can drive a rover around and look for fossils or organic molecules on the surface. The oceans of Europa and Enceladus are buried beneath miles of ice. We cannot see inside them, we cannot touch them, and drilling through the ice would be one of the most difficult engineering challenges ever attempted. So how do we find life without going there? One possibility is to study the plumes. On Enceladus, and possibly on Europa, water from the ocean is being ejected into space through geysers and plumes. A spacecraft could fly through these plumes and collect samples, analyzing them for signs of life. What would we look for? There are several possibilities. First, we could look for organic molecules, particularly complex ones like amino acids, lipids, or sugars. These are the building blocks of life, and if we find them in the plumes, it would be strong evidence that organic chemistry is happening in the ocean. Second, we could look for patterns in the molecules that suggest biological activity. On Earth, life has a preference for certain isotopes over others. For example, living organisms preferentially use carbon-12 over carbon-13 because carbon-12 is slightly lighter and easier to incorporate into organic molecules. If we find organic molecules in the plumes that show the same isotopic signature, it could be a sign of life. Third, we could look for the molecules themselves. If we find amino acids, we could check whether they are left-handed or right-handed. On Earth, life uses exclusively left-handed amino acids. If we find a mixture of left-handed and right-handed amino acids in the plumes, that would suggest they are not biological. But if we find only left-handed amino acids, that would be strong evidence of life. Finally, we could look for the organisms themselves. If life exists in the ocean, there is a chance that living cells could be carried up in the plumes and ejected into space. A spacecraft equipped with a high-resolution microscope could potentially capture these cells and image them directly. This is an incredibly ambitious goal, but it is not impossible. Of course, detecting life is one thing. Proving that it is life is another. Even if we find organic molecules or cell-like structures in the plumes, we would need to rule out non-biological explanations. Chemistry can produce complex molecules without life. Minerals can form structures that look like cells. We would need multiple lines of evidence, and we would need to be very careful not to contaminate the samples with microbes from Earth. But if we do find life, if we can prove beyond a reasonable doubt that there are living organisms in the oceans of Europa or Enceladus, it would be one of the most important discoveries in human history. It would answer the ancient question, are we alone? And the answer would be no. We are not alone. Life exists elsewhere in the solar system. And if it exists here, it probably exists throughout the galaxy. That is the prize. That is what drives scientists to plan these ambitious missions, to develop new technologies, to push the boundaries of what is possible. And in the next chapter, we are going to talk about those missions, the spacecraft we are building, the challenges we face, and the incredible journey that lies ahead as we prepare to explore the hidden oceans of the outer solar system. We have talked about the discovery of the ocean worlds, the evidence that they are habitable, and the tantalizing possibility that they might harbor life. But all of this remains theoretical until we actually go there and explore these oceans directly. So what are the plans? What missions are in the works? And what are the incredible challenges that engineers and scientists face as they prepare to visit these distant worlds? The first thing to understand is that exploring ocean worlds is not easy. These are some of the most difficult places in the solar system to reach and study. They are hundreds of millions of miles from Earth. They are covered in thick shells of ice, and they orbit in environments filled with intense radiation. Every aspect of a mission to an ocean world requires cutting-edge technology and careful planning. Let us start with the missions that are already approved and in development. The first is NASA's Europa Clipper mission, which is scheduled to launch in October 2024 and arrive at Jupiter in April 2030. This is one of the most ambitious missions NASA has ever undertaken. Europa Clipper is not an orbiter in the traditional sense. Instead, it will orbit Jupiter and make dozens of close flybys of Europa, each one bringing the spacecraft within a few tens of miles of the Moon's surface. Why flybys instead of an orbit around Europa? The answer is radiation. Jupiter's magnetosphere is incredibly powerful, and Europa orbits right in the middle of it. The radiation levels at Europa are so intense that they would quickly fry the electronics of any spacecraft that stayed there for long. By orbiting Jupiter and only making brief flybys of Europa, the Clipper spacecraft can limit its exposure to radiation and survive for years. During each flyby, Europa Clipper will use a suite of sophisticated instruments to study the Moon. It will have cameras to map the surface in high resolution. It will have a radar system that can penetrate the ice and see structures below the surface, possibly even detecting the ocean itself. It will have a magnetometer to measure Europa's magnetic field and refine our understanding of the ocean's depth and salinity. And it will have mass spectrometers to analyze any gas or particles around Europa, searching for signs of plumes like those on Enceladus. If Europa Clipper does detect plumes, it will fly through them and collect samples, analyzing them for organic molecules, salts, and other chemicals. This could give us our first direct look at the composition of Europa's ocean without ever landing on the surface. But Europa Clipper is just the beginning. The European Space Agency is also planning a mission called JUICE, or JUICE, which stands for Jupiter Icy Moons Explorer. JUIC launched in April 2023 and will arrive at Jupiter in July 2031. Like Europa Clipper, JUICE will make flybys of Europa, but its primary target is Ganymede. JUICE will eventually enter orbit around Ganymede, becoming the first spacecraft ever to orbit a moon other than Earth's moon. JUIC. It will study Ganymede's surface, its magnetic field, and its subsurface ocean. It will also make flybys of Callisto, studying that moon's potential ocean as well. Together, Europa Clipper and JUICE will give us an unprecedented view of Jupiter's ocean worlds. But as exciting as these missions are, they are still just reconnaissance. They will study the oceans from above, but they will not touch the water. To truly explore these oceans, we need to go deeper. We need to land on the surface, drill through the ice, and send a probe into the ocean itself. That is the goal of future missions, and scientists are already working on the technology to make it happen. One concept is called the Europa Lander. This would be a spacecraft that lands on Europa's surface and uses a drill or a melting probe to penetrate the ice. The drill would go as deep as possible, perhaps 30 feet or more, and collect samples of the ice and any liquid water it encounters. The lander would then analyze these samples using onboard instruments, searching for signs of life. But drilling through Europa's ice is an enormous challenge. The ice is as hard as rock, and it is incredibly cold. Drills designed for Earth would not work in these conditions. Engineers are developing special drills that use heat to melt through the ice, or that use rotating blades made of incredibly hard materials. They are also developing robotic systems that can operate autonomously, because the time delay between Earth and Europa is more than 40 minutes. You cannot control a robot in real time when it takes 40 minutes for a signal to travel one way. Even more ambitious is the concept of a Europa submarine, sometimes called the Europa Ocean Explorer. This would be a small, autonomous submarine that would melt through the ice shell and then swim freely in the ocean below. The submarine would be equipped with cameras, sensors, and sampling equipment, and it would explore the ocean, searching for hydrothermal vents, microbial life, or anything else of interest. Building such a submarine is a monumental engineering challenge. It would need to be small and light enough to fit on a spacecraft, yet robust enough to survive the journey to Jupiter and the harsh conditions of Europa's ocean. It would need to navigate autonomously, because there would be no way to communicate with it once it was beneath the ice. And it would need a power source that could last for months or even years, because there is no sunlight in the ocean and no way to recharge. Scientists are exploring several options. One is to use nuclear power, a radioactive isotope that generates heat and electricity through radioactive decay. Another option is to develop advanced batteries or fuel cells that can store enough energy for the mission. Engineers are also developing sonar systems that the submarine could use to navigate, and eye systems that would allow it to make decisions on its own. NASA is also considering a mission to Enceladus. Because Enceladus has plumes that are constantly ejecting ocean material into space, a mission to Enceladus might be simpler than a mission to Europa. A spacecraft could orbit Enceladus and repeatedly fly through the plumes, collecting samples and analyzing them. It would not need to land, and it would not need to drill through the ice. One proposed mission is called the Enceladus Orbolander. This spacecraft would orbit Enceladus for several years, flying through the plumes dozens of times and collecting as much data as possible. Then, at the end of the mission, it would land on the surface near the Tiger Stripes and use instruments to study the ice and search for organic molecules. Another concept is the Enceladus Life Finder, or ELF, or ELF, which would focus specifically on detecting life. ELF would carry instruments capable of analyzing the plumes for amino acids, lipids, and other biosignatures. It would also carry a microscope that could potentially image living cells if they are present in the plume material. These missions are still in the planning stages, and it will be years before they are approved and funded. But the technology is advancing rapidly, and scientists are optimistic that we will be exploring these oceans within our lifetimes. There is also exciting work being done here on Earth to prepare for these missions. Scientists are developing and testing technologies in extreme environments on our own planet that mimic the conditions on ocean worlds. One of the most important test sites is Antarctica. The ice sheets of Antarctica are similar in many ways to the ice shells of Europa and Enceladus. They are thick, they are cold, and they cover bodies of liquid water, including subglacial lakes like Lake Vostok, which has been isolated beneath 2 miles of ice for millions of years. Scientists have drilled into some of these subglacial lakes and found that they contain microbial life, even in complete darkness and isolation. These discoveries have important implications for the search for life on ocean worlds. If life can survive in the subglacial lakes of Antarctica, it could survive in the oceans of Europa or Enceladus. Researchers are also testing drilling equipment and submarines in Antarctica. They have developed a device called a cryobot, a heated probe that melts through ice, leaving a thin layer of water behind it as it descends. The cryobot is designed to be attached to a tether, which provides power and communication. Once the cryobot reaches the subglacial lake, it would deploy a hydrobot, a small submarine that would explore the lake and collect samples. These technologies are still being refined, but they represent the future of ocean world exploration. If we can make them work on Earth, we can adapt them for use on Europa or Enceladus. There is also exciting work being done on autonomous navigation and artificial intelligence. A submarine exploring the ocean of Europa would need to make decisions on its own without human input. It would need to avoid obstacles, navigate toward areas of interest, and manage its power and resources. Engineers are developing AI systems that can do all of this, and they are testing them in underwater environments on Earth, from the deep ocean to ice-covered lakes. One of the most ambitious projects is called the BRUI, the Buoyant Rover for Under-Ice Exploration. BRUI is a small buoyant robot that is designed to drive along the underside of ice, exploring the interface between the ice and the water. This is an important region because on Earth, the underside of ice is often teeming with life. Algae, bacteria, and small animals cling to the ice, feeding on nutrients and sunlight that filters through. On Europa or Enceladus, there would be no sunlight, but the underside of the ice could still be an interesting place to explore. It might be where ocean water interacts with the ice shell, where cracks and fissures form, and where chemicals from the ocean are concentrated. BRUI has been tested in the Arctic and in Antarctica, and it has proven to be an effective tool for exploring ice-covered environments. All of these technologies are being developed with one goal in mind: to explore the hidden oceans of the outer solar system and search for life. But there is one more challenge we need to talk about, and it is perhaps the most important of all. That challenge is planetary protection. Planetary protection is the practice of preventing contamination of other worlds with life from Earth, and preventing contamination of Earth with potential life from other worlds. This is critical for two reasons. First, we do not want to accidentally bring Earth microbes to Europa or Enceladus and contaminate those pristine environments. If we find life there, we want to be sure it is native life, not something we brought with us. Second, if there is life on these ocean worlds, we need to be careful not to bring it back to Earth in a way that could be dangerous. This is less of a concern for microbial life, but it is still something we need to think about carefully. NASA and other space agencies have strict planetary protection protocols. Any spacecraft that goes to an ocean world must be carefully sterilized before launch. The spacecraft is baked in ovens, bathed in chemicals, and tested to ensure that it is as clean as possible. Even so, it is impossible to completely sterilize a spacecraft. There will always be a few microbes that survive. The goal is to reduce the number of microbes to a level where the risk of contamination is extremely low. For missions that will land on the surface or drill into the ice, the planetary protection requirements are even stricter. The landing site must be chosen carefully to avoid areas where the ice is thin and the ocean is close to the surface. The drill or cryobot must be designed to avoid cross-contaminating the ocean if it breaks through the ice. These are difficult challenges, but they are not insurmountable. Scientists have been dealing with planetary protection for decades, and they have developed rigorous protocols and technologies to minimize the risk of contamination. So here is where we stand. We have discovered that the outer solar system is filled with ocean worlds, some of which might be habitable. We have missions in development to study these worlds in detail, and we are developing the technology to explore their oceans directly. Within the next few decades, we could have submarines swimming in the oceans of Europa or Enceladus, searching for life. This is not science fiction. This is happening right now. And the next chapter of this story will be written by the missions and discoveries that are just around the corner. Let us pause again and think about the deep. Not the deep of Earth's oceans, but the deep of these alien seas. The oceans beneath the ice of Europa, Enceladus, and the other ocean worlds are not like any ocean on Earth. On Earth, our oceans are connected to the surface. Sunlight penetrates the upper layers, warming the water and driving photosynthesis. Storms stir the surface, mixing oxygen and nutrients. The ocean is dynamic, constantly changing with the seasons, with the tides, with the weather. But the oceans of the outer solar system are different. They are sealed beneath miles of ice, completely isolated from the space above. No sunlight ever reaches them. No storms disturb their surfaces. They exist in eternal darkness and silence, unchanging for millions of years. What would it be like to float in one of these oceans? Imagine you are descending through the ice of Europa, passing through layer after layer of frozen water. At first, the ice is clear, almost transparent, but as you go deeper, it becomes more opaque, filled with tiny fractures and impurities. The pressure increases with every meter you descend, pressing in on you from all sides. And then, suddenly, you break through. You are no longer in ice. You are in water. Liquid water, dark and cold, and perfectly still. There is no current here, no waves, no movement of any kind. The water is so clear that your lights shine into the distance, but they reveal nothing except more darkness. You descend deeper, and the pressure continues to build. The water around you is cold, just above the freezing point, but it does not freeze because of the pressure and the dissolved salts. You pass through the thermocline, the boundary between the cold upper water and the warmer water below. Yes, warmer. Not warm like a tropical sea on Earth, but warmer than the ice above. As you descend farther, you begin to sense something. A faint vibration in the water, a distant rumble. You are approaching the sea floor, and somewhere down there is activity. Hydrothermal vents, perhaps, or tidal flexing of the rocky interior, creating earthquakes that send tremors through the water. And then you see it. A faint glow, like the light of a distant fire. You move toward it, and the glow becomes brighter. It is a hydrothermal vent, a crack in the sea floor where hot water is pouring out, heated by the interior of the moon. The water around the vent is warm, perhaps 200 degrees Fahrenheit, and it is filled with dissolved minerals that precipitate out as the hot water mixes with the cold ocean, creating towering chimneys of rock and mineral. And there, clinging to the rocks, you see them. Structures, shapes, things that might be alive. They are not moving, not obviously, but they are there, and they are unlike anything you have ever seen. This is the dream. This is what awaits us in the hidden oceans of the outer solar system. a frontier as vast and mysterious as any on Earth, filled with possibilities, filled with wonder, and we are on the verge of exploring it. So far, we have focused on the ocean worlds in our own solar system, but the universe is vast, and our solar system is just one tiny speck in a galaxy of hundreds of billions of stars. If ocean worlds are common here, how common might they be out there, around other stars? This question has become one of the most exciting frontiers in astronomy. In the past 3 decades, scientists have discovered thousands of planets orbiting other stars, called exoplanets. Some of these planets are hot Jupiters, gas giants that orbit very close to their stars. Others are super-Earths, rocky planets larger than Earth but smaller than Neptune. And some are in the habitable zone, the region around a star where temperatures are just right for liquid water to exist on the surface. But as we have learned from Europa and Enceladus, liquid water does not have to be on the surface. It can exist beneath the surface, hidden under layers of ice, kept liquid by internal heat. If this is possible in our solar system, it must also be possible around other stars. And if that is true, then ocean worlds might be the most common type of habitable world in the galaxy. Let us start by looking at the kinds of exoplanets we have discovered and think about which ones might be ocean worlds. The first category is ice giants. These are planets similar to Uranus and Neptune, with thick atmospheres of hydrogen, helium, and methane, and icy interiors. We have discovered many of these kinds of planets around other stars, and some of them are in the habitable zone, or close to it. If these planets have large moons, those moons could be ocean worlds, just like the moons of Jupiter and Saturn. The second category is super-Earths and mini-Neptunes. These are planets that are larger than Earth, but smaller than Neptune. They are incredibly common in the galaxy, far more common than Earth-sized planets. Scientists believe that many of these planets have thick layers of water ice, possibly with liquid water oceans beneath the ice. One of the most famous examples is a planet called K218b. This planet orbits a red dwarf star about 120 light-years from Earth, and it is about twice the size of Earth, with about 8 times the mass. In 2019, scientists announced that they had detected water vapor in the atmosphere of K218b using the Hubble Space Telescope. This was the first time water vapor had been detected in the atmosphere of a planet in the habitable zone. At first, this discovery was hailed as a major step toward finding life beyond Earth. But as scientists studied K218b more closely, they realized that it is probably not an Earth-like world. Instead, it is likely a mini-Neptune with a thick hydrogen atmosphere and possibly a deep water ocean beneath. The surface pressure would be enormous, thousands of times greater than Earth's atmospheric pressure, which would make it very difficult for life as we know it to exist. But then, in 2021, a new idea emerged. Some scientists proposed that K218b might not be a mini-Neptune, but instead a Hycean world. Hycean stands for hydrogen and ocean, and it refers to a type of planet with a thick hydrogen atmosphere and a liquid water ocean beneath. These planets would be very different from Earth, but they might still be habitable, especially in the upper layers of the ocean, where the temperature and pressure are more moderate. In 2023, scientists used the James Webb Space Telescope to study K2-18b in even greater detail. They detected not only water vapor, but also methane and possibly dimethyl sulfide, a molecule that on Earth is only produced by living organisms. This is not proof of life, but it is intriguing, and it has sparked intense debate about whether Hycean worlds could be habitable. The truth is, we do not know yet. Hycean worlds are a new concept, and we are only beginning to understand what they might be like. But they represent a new category of potentially habitable worlds, one that could be much more common in the galaxy than Earth-like planets. Another category of exoplanet ocean worlds is rogue planets. These are planets that do not orbit any star. They have been ejected from their planetary systems and now wander through interstellar space, alone in the darkness. You might think that a planet without a star would be frozen solid, but that is not necessarily true. If a rogue planet has a thick atmosphere and a lot of internal heat, it could maintain liquid water oceans beneath an icy crust, just like Europa or Enceladus. The internal heat could come from radioactive decay in the planet's core, or from tidal heating if the planet has large moons. Scientists estimate that there could be billions of rogue planets in the Milky Way, and some of them might be ocean worlds. In 2021, scientists announced the discovery of a candidate rogue planet about the size of Earth, using a technique called gravitational microlensing. This technique detects planets by the way their gravity bends and magnifies the light from background stars. The discovery suggests that small rogue planets are common, and if they are common, then rogue ocean worlds might be common too. This is a mind-blowing idea. There could be entire worlds out there, drifting through the darkness of space, with no sun, no starlight, but still harboring oceans and potentially life. These worlds would be incredibly difficult to detect and study, but they might be some of the most common habitable environments in the galaxy. Now, let us think about the moons of exoplanets. Just like Jupiter and Saturn have ocean moons, it is likely that many exoplanets also have moons, and some of those moons could be ocean worlds. Detecting exomoons is incredibly difficult because they are much smaller than the planets they orbit, and their signals are very faint. But scientists have developed techniques to search for them, and there have been a few tentative detections. None of these detections have been confirmed yet, but it is only a matter of time before we find the first exomoon. If we do find an exomoon, and if we can study it in detail, we might be able to determine whether it has a subsurface ocean. We would look for the same kinds of signatures that we use to detect oceans in our own solar system. Induced magnetic fields, gravitational anomalies, and possibly even plumes of water vapor. The discovery of an ocean world around another star would be a monumental achievement, because it would show that ocean worlds are not just a feature of our solar system, but a common phenomenon throughout the galaxy. And if ocean worlds are common, then the potential for life in the universe is far greater than we ever imagined. But there is one more category of exoplanet that we need to talk about, and it is perhaps the most intriguing of all. These are ocean planets, worlds where the entire surface is covered in a deep water ocean, with no continents, no dry land, just water, possibly hundreds of miles deep. On Earth, about 71% of the surface is covered by water, but the water is relatively shallow, with an average depth of about 2.3 miles. But imagine a planet where the water is 100 miles deep or 500 miles deep. The pressure at the bottom of such an ocean would be so great that the water would turn into exotic forms of ice that only exist at extreme pressures. These ocean planets might form in the outer regions of planetary systems, where there is a lot of water ice, and then migrate inward toward the star. As they get closer to the star, the ice melts, and the entire planet becomes covered in a global ocean. Some scientists believe that ocean planets could be quite common, especially around red dwarf stars, which are the most common type of star in the galaxy. Red dwarfs are smaller and cooler than the Sun, and their habitable zones are much closer to the star. Planets in these habitable zones would receive just enough heat to maintain liquid water on the surface, but they would probably be tidally locked, meaning one side always faces the star and the other side always faces away. On a tidally locked ocean planet, the sun-facing side would be hot, possibly with constant storms and hurricanes, while the night side would be cold, possibly frozen. The terminator, the boundary between day and night, might be the most habitable region with moderate temperatures and stable conditions. Could life exist on an ocean planet? It is possible. Life in such an ocean would not have access to land, to rocks, to minerals, or to many of the resources that life on Earth depends on, but it might still find a way. There could be floating ecosystems, similar to the mats of sargassum seaweed in Earth's oceans. There could be life that feeds on dissolved nutrients and minerals in the water. There could even be life that uses the temperature gradient between the hot surface and the cold depths as a source of energy. These are speculative ideas, but they are based on solid science. The more we learn about exoplanets, the more we realize that the universe is filled with worlds that are unlike anything we have on Earth, and yet they might still be capable of supporting life. So here is the big picture. In our solar system, we have at least 6 ocean worlds, and possibly more. In the galaxy, there are probably trillions of ocean worlds, ranging from icy moons like Europa and Enceladus, to Hycean worlds like K218b, to rogue planets drifting through interstellar space, to ocean planets covered entirely in water. If even a tiny fraction of these ocean worlds are habitable, and if even a tiny fraction of those habitable worlds have developed life, then the universe could be teeming with life. Not life on the surface, where we can see it with telescopes, but life hidden beneath the surface, in oceans that are isolated and protected, where evolution has had billions of years to work its magic. This is the new paradigm in the search for life beyond Earth. We are no longer just looking for Earth-like planets in the habitable zone. We are looking for ocean worlds, wherever they might be, and we are realizing that the potential for life is far greater than we ever imagined. And that brings us to the final part of this story. What does all of this mean for us, for humanity, for our understanding of our place in the universe? We have journeyed far in this story. We have traveled from the discovery of Europa's smooth, icy surface to the erupting geysers of Enceladus, from the subsurface oceans of Ganymede and Titan to the possibility of ocean worlds around distant stars. We have explored the chemistry of life, the technology of exploration, and the incredible challenges that lie ahead. But before we finish, let us step back and ask a bigger question. What do these discoveries mean? How do they change the way we see the universe and our place in it? First, the discovery of ocean worlds has fundamentally changed our understanding of where life can exist. For most of human history, we thought that life needed a planet like Earth, a world with a solid surface, a thick atmosphere, and a star to provide warmth and light. The habitable zone, the region around a star where temperatures are just right for liquid water, was thought to be the only place where life could thrive. But Europa and Enceladus have shown us that this is not true. Life does not need a warm, sunny planet. It does not need to be in the habitable zone. It can exist in the frozen darkness of the outer solar system, in oceans buried beneath miles of ice, powered by chemistry rather than sunlight. This realization has profound implications. It means that the number of potentially habitable worlds in the universe is far greater than we ever imagined. It means that life might be common, not rare. And it means that when we search for life beyond Earth, we need to think bigger, broader, and more creatively than we ever have before. Second, the discovery of ocean worlds teaches us something important about Earth. Our planet is special, not because it is the only world with water, but because it is one of the few worlds where water exists on the surface, exposed to the atmosphere and the sunlight. This makes Earth unique in our solar system, and possibly unique in the galaxy. But it also makes Earth fragile. The water on Earth's surface is not protected by a thick shell of ice. It is vulnerable to changes in temperature, to changes in the atmosphere, to asteroid impacts and solar flares. The fact that Earth has maintained liquid water on its surface for billions of years is a testament to the delicate balance of forces that have kept our planet habitable. When we look at the ocean worlds of the outer solar system, we see a different kind of stability. These oceans are protected, sealed beneath ice, isolated from the chaos of the surface. They have remained liquid for billions of years, not because of a delicate balance, but because of a robust mechanism, tidal heating. As long as the moons remain in their orbits, the oceans will remain liquid. This raises an interesting question. Is it better to have water on the surface where it is exposed and vulnerable, or beneath the surface where it is protected and stable? For life, both have advantages and disadvantages. Surface water has access to sunlight, which drives photosynthesis and provides abundant energy. But subsurface water is protected from radiation, from temperature extremes, and from the vacuum of space. On Earth, life benefits from surface water, and it has thrived in a way that might not be possible on an ocean world. But on an ocean world, life might persist longer because the environment is more stable and less susceptible to catastrophic changes. Third, the discovery of ocean worlds forces us to confront a profound philosophical question. If life exists in the oceans of Europa or Enceladus, what does that mean for our understanding of life itself? On Earth, all life is connected. We all share a common ancestor, a single organism that lived billions of years ago. We are all part of the same family tree, built from the same genetic code, using the same biochemistry. But if we find life on Europa, it will be completely independent of life on Earth. It will have a different origin, a different evolutionary history, and possibly a different biochemistry. This would be the discovery of a second genesis, a second origin of life. And if life can arise independently on two different worlds in the same solar system, then it must be common throughout the universe. The universe must be filled with countless geneses, countless experiments in biochemistry and evolution. What would this do to our understanding of life? It would show us that life is not a cosmic accident, but a natural consequence of chemistry and physics. It would show us that wherever the conditions are right, life will emerge. And it would show us that we are not alone, not unique, but part of a much larger story that spans the entire universe. Fourth, the discovery of ocean worlds teaches us something about the nature of exploration and discovery. The story of Europa and Enceladus is a story of curiosity, of human ingenuity, of the drive to explore the unknown. When Voyager 1 flew past Jupiter in 1979, nobody expected to find an ocean world. Europa was just one moon among many, a tiny point of light in a crowded system. But scientists looked at the images, asked questions, proposed hypotheses, and followed the evidence wherever it led. And what they found was one of the most important discoveries in the history of planetary science. This is the essence of science. It is not about having all the answers. It is about asking the right questions and being willing to follow the evidence, even when it leads to places you never expected. It is about being open to the possibility that the universe is stranger and more wonderful than you ever imagined. And it is about persistence. The journey from the discovery of Europa's smooth surface to the confirmation of its subsurface ocean took decades. It required multiple missions, multiple lines of evidence, and the work of thousands of scientists and engineers. But they kept going, kept pushing, kept refining their understanding until the picture became clear. This is the same spirit that will take us to the next level of exploration. The missions we are planning today, the Europa Clipper, JUICE, the Enceladus Orbilander, are the result of decades of work, and they will lay the groundwork for the missions that come after. One day, perhaps in our lifetimes, we will send a submarine into the ocean of Europa or Enceladus, and what we find there will rewrite the textbooks and change the way we see the universe. Fifth, the discovery of ocean worlds reminds us of the incredible diversity of worlds in the universe. No two planets or moons are alike. Europa is not the same as Enceladus. Ganymede is not the same as Titan. Each world has its own unique characteristics, its own geology, its own chemistry, and its own story. This diversity is one of the most beautiful aspects of planetary science. The universe is not a uniform place filled with identical copies of Earth. It is a tapestry of different worlds, each one shaped by different forces, each one with its own history and its own potential. And yet, despite this diversity, there are commonalities. Water is everywhere. Chemistry is universal. The laws of physics are the same on every world. This means that even though the universe is diverse, it is also comprehensible. We can study these distant worlds. We can understand them, and we can learn from them. Finally, the discovery of ocean worlds gives us hope. In a universe that is vast and often cold and indifferent, the idea that there are worlds out there with oceans, with chemistry, with the potential for life, is deeply comforting. It reminds us that we are part of something larger. We are not isolated, not alone, but connected to the rest of the universe through the same fundamental processes that shape every world. The water in Europa's ocean came from the same cosmic cloud that formed the sun and the planets, the same cloud that gave birth to Earth and all its oceans. In a very real sense, we are made of the same stuff as Europa and Enceladus. The atoms in our bodies were forged in the hearts of stars, scattered across the galaxy, and eventually came together to form the planets and moons of our solar system. We are stardust, and so is everything else. This cosmic perspective can be humbling, but it is also empowering. It reminds us that we have the ability to understand the universe, to explore it, to learn from it. And it reminds us that the search for life is not just a scientific endeavor, but a deeply human one. It is about seeking connection, seeking understanding, seeking to know whether we are alone or whether there are others out there living their own lives in their own oceans, beneath their own skies. The discovery of ocean worlds has given us a new direction in that search. We are no longer just looking out at the stars, hoping to find a planet like Earth. We are looking closer to home, at the moons of Jupiter and Saturn, and we are realizing that the answers we seek might be hiding just beneath the surface, waiting for us to dig a little deeper, to explore a little farther, to ask the next question. And that is the spirit of exploration. It is not about having all the answers. It is about the journey. It is about the thrill of discovery. It is about standing on the edge of the unknown and taking that next step forward into the darkness, toward the light. Now, let us imagine the future. Not the distant future, but the near future. A time, perhaps 20 or 30 years from now, when the missions we are planning today have borne fruit, when the technology we are developing has matured, when humanity finally takes the next great step in the exploration of the solar system. The year is 2045. The Europa Clipper mission completed its survey in the mid-2030s, confirming the presence of plumes at Europa's south pole and mapping the ice shell in unprecedented detail. The data showed that the ice is thinnest near the plumes, only about 3 miles thick in some places, making it a prime target for a landing mission. In 2038, NASA, in partnership with ESA and other international space agencies, launched the Europa Explorer mission. This mission carries 2 components, a lander and a cryobot. The journey to Jupiter takes 6 years, and now, in early 2045, the spacecraft is entering orbit around Europa. The world watches as the lander separates from the orbiter and begins its descent. There is no atmosphere on Europa, so there are no parachutes, no aerodynamic braking. The lander uses rockets to slow itself down, and the final approach is tense. Europa's surface is covered in ridges and cracks, and the landing site has been chosen carefully to avoid the most hazardous terrain. And then, contact. The lander touches down on the ice of Europa, and for the first time in history, a human-made object is sitting on the surface of an ocean world other than Earth. For the first few days, the lander operates from the surface. It deploys cameras and takes panoramic images of the alien landscape. The sky is black, and Jupiter looms enormous on the horizon, a swirling sphere of orange and brown, brighter than a full moon on Earth. The surface is crisscrossed with dark streaks and ridges, frozen waves of ice that have been shaped by forces from below. The lander also deploys instruments to measure the composition of the ice and search for organic molecules. The results are astonishing. The ice contains not just water, but salts, sulfur compounds, and complex organic molecules, including amino acids. This is the first direct confirmation that the building blocks of life are present on Europa. But the real mission is only beginning. On the 5th day, the lander deploys the cryobot, a cylindrical probe about 6 feet long and 1 foot in diameter. The cryobot is heated by a small nuclear reactor, and it uses that heat to melt through the ice. It begins its descent slowly, carefully, melting a narrow tunnel through the ice as it goes. The progress is slow. The cryobot descends at a rate of about 30 feet per day, and it is tethered to the lander by a thin fiber optic cable that provides power and communication. The world waits. Days turn into weeks, and weeks turn into months. The cryobot continues its descent, sending back data on the temperature and composition of the ice as it goes. At a depth of about half a mile, the cryobot encounters a layer of fractured ice, a region where the ice has been broken and refrozen multiple times. This is a sign of tidal activity, a sign that the ocean below is connected to the surface through cracks and fissures. And then, on day 87 of the cryobot's descent, something changes. The temperature suddenly increases. The pressure drops. The cryobot has broken through. It is no longer in ice. It is in water. It has reached the ocean of Europa. The moment is electric. Around the world, people are glued to their screens, watching the live feed from the cryobot. The camera activates, and for the first time, humanity sees the ocean of another world. At first, there is only darkness. The cryobot's lights shine into the water, but they reveal nothing except blackness and tiny particles suspended in the water. The cryobot deploys its instruments, measuring the temperature, the salinity, the dissolved gases. The water is cold, just above the freezing point, and it is salty, about twice as salty as Earth's oceans. The cryobot releases a small hydrobot, a miniature submarine the size of a football. The hydrobot is untethered, completely autonomous, equipped with cameras, sensors, and a sonar system. It begins to swim, slowly at first, testing its systems, and then more confidently, moving away from the cryobot and into the open ocean. The hydrobot descends deeper and deeper, sending back data as it goes. The ocean is vast, much larger than anyone expected. The sonar shows that the seafloor is more than 50 miles below, far deeper than Earth's oceans. The water is stratified, with layers of different temperature and salinity. And then, after hours of descent, the hydrobot detects something. A faint sound, a rhythmic thumping, like a heartbeat. The hydrobot's sonar shows a structure ahead, something rising from the seafloor. The hydrobot approaches cautiously, and as it gets closer, the structure becomes clearer. It is a hydrothermal vent, a towering chimney of rock and mineral, dozens of feet tall, with hot water pouring out of the top. The water around the vent is warm, more than 200 degrees Fahrenheit, and it is filled with dissolved minerals that precipitate out as the hot water mixes with the cold ocean. And there, clinging to the sides of the vent, are structures. They are not rocks. They are not minerals. They are something else. Something organic. The hydrobot moves closer, its camera zooming in. The structures are tubular, pale white, and they seem to be growing out of the rock. They are covered in a thin film, possibly a biofilm, and they are surrounded by smaller structures that might be microbial mats. The hydrobot deploys a sampling arm and carefully collects a piece of one of the tubular structures. It places the sample in a sealed container and begins the analysis. The instruments detect organic molecules, complex ones, including amino acids, lipids, and something that looks like a nucleotide, a building block of DNA, or RNA. And then the hydrobot's microscope activates. It examines a drop of water from the sample, and what it sees is unmistakable. Cells, living cells. They are small, only a few micrometers across, but they are there. They have cell walls, they have internal structure, and they are moving, propelled by tiny hair-like structures called flagella. This is it. This is the moment humanity has been waiting for. Life, not on Earth, but on another world. Life that evolved independently in the hidden ocean of Europa, in complete darkness, powered by chemistry rather than sunlight. The discovery is confirmed, verified, and announced to the world. It is the most important scientific discovery in human history, and it changes everything. Because if life exists on Europa, and if life can arise independently on two different worlds in the same solar system, then life must be common in the universe. The cosmos is not empty. It is teeming with life, hidden beneath the surfaces of countless ocean worlds, thriving in environments that we are only beginning to understand. This is not science fiction. This is the future we are building toward. Every mission we launch, every instrument we develop, every experiment we conduct, brings us one step closer to this moment. And when that moment comes, when we finally touch the ocean of Europa or Enceladus and find life, it will be a moment of profound significance. It will be a moment when humanity realizes that we are not alone, that we are part of a much larger story, that the universe is filled with mystery and wonder and beauty. And it will be a moment when we understand, truly understand, that the search for life is not just about finding microbes on a distant moon. It is about understanding our place in the cosmos. It is about realizing that we are connected to every living thing, not just on Earth, but throughout the universe. It is about recognizing that the same forces that created us have created life elsewhere, and that the universe is not a cold, dead place, but a living, breathing, evolving tapestry of life. This is the promise of the ocean worlds. This is the future that awaits us. And it begins now with the missions we are planning, the questions we are asking, and the dreams we are daring to dream. So here we are at the end of this journey. We have traveled from the discovery of Europa's strange, smooth surface to the erupting geysers of Enceladus. We have explored the subsurface oceans of Ganymede, Callisto, and Titan. We have ventured beyond our solar system to imagine ocean worlds around distant stars. And we have stood at the edge of the future, imagining the day when humanity finally touches the ocean of another world. But this is not really the end. It is just the beginning. The story of the ocean worlds is still being written. Every year, we learn something new. Every mission brings back data that surprises us, challenges us, and expands our understanding of what is possible. The Europa Clipper mission will launch soon, and it will give us our most detailed look yet at Europa's ocean. The JUICE mission will explore Ganymede and reveal the secrets of its subsurface sea. And in the decades to come, we will send landers, submarines, and robotic explorers to dive beneath the ice and search for life. These missions are not just about science. They are about humanity's innate drive to explore, to discover, to push beyond the boundaries of what we know. They are about asking the deepest questions we can ask and being willing to follow the answers wherever they lead. And they are about hope. In a world that can often feel divided and uncertain, the search for life on ocean worlds reminds us of what we can achieve when we work together. The missions to Europa, Enceladus, and the other ocean worlds are international efforts, involving scientists and engineers from dozens of countries. They are funded by governments and supported by people around the world who share a common dream: to find life beyond Earth. This dream is not just for scientists. It is for everyone, because the discovery of life on another world would belong to all of humanity. It would be a moment when we realize that we are not isolated, not alone, but part of a cosmic community of living worlds. So what can you do? How can you be part of this story? First, stay curious. Keep asking questions. Keep learning about the ocean worlds and the missions to explore them. Follow the Europa Clipper mission as it journeys to Jupiter. Watch for news about JUICE and its exploration of Ganymede. Read about the new discoveries that scientists are making every day. Second, support space exploration. Whether that means advocating for funding for NASA and other space agencies, or supporting private companies and organizations that are working to explore the solar system, your voice matters. Space exploration is expensive and difficult, but it is also one of the most important things humanity can do. It expands our knowledge, inspires future generations, and brings us together in a common goal. Third, think about what these discoveries mean. Think about the fact that there are oceans out there, larger than all of Earth's oceans combined, hidden beneath the ice of distant moons. Think about the possibility that those oceans might harbor life, life that evolved independently of Earth, life that could teach us something profound about the nature of biology and the universe. And think about what it would mean to find that life. It would not just be a scientific achievement. It would be a philosophical and spiritual milestone, a moment when humanity takes its place as a true citizen of the cosmos. The ocean worlds are out there, waiting for us. They are vast, ancient, and filled with possibility. They challenge our assumptions, expand our imagination, and remind us that the universe is far more wonderful than we ever dared to believe. And the journey to explore them has only just begun. So as you go about your day, as you look up at the night sky, remember that out there, beyond the stars you can see, there are worlds with oceans. Oceans that have never seen sunlight. Oceans that are kept liquid by forces we are only beginning to understand. Oceans that might be teeming with life. And remember that we, humanity, are on the verge of exploring those oceans. We are building the spacecraft, developing the technology, and asking the questions that will take us there. We are living in a time of incredible discovery, a time when the impossible is becoming real. This is the age of ocean worlds, and you are here to witness it. Thank you for joining me on this journey. Thank you for your curiosity, your wonder, and your willingness to dream. The universe is vast, but it is also knowable. The answers are out there, hidden beneath the ice, waiting for us to find them. And when we do find them, when we finally dive beneath the ice and touch the water of an alien ocean, it will be one of the greatest moments in human history. A moment when we realize that we are not alone. A moment when we understand that the universe is filled with life, with mystery, with beauty. That moment is coming, and it begins with the questions we ask today, the missions we launch tomorrow, and the discoveries we make in the years to come. The hidden ocean world is calling, and humanity is ready to answer. If you enjoyed this journey to the ocean worlds, please consider subscribing to this channel. We have many more cosmic mysteries to explore together, from the birth of stars to the fate of the universe, from the search for extraterrestrial intelligence to the physics of black holes. Every week, we dive deep into the most fascinating questions in space and science. And if you found this video thought-provoking, share it with someone who loves science, who dreams about space, who wonders about life beyond Earth. Let's keep this conversation going. Let's keep exploring. Let's keep asking questions. Because the universe is waiting, and the story of the ocean worlds is just beginning. Thank you for watching. And remember, the cosmos is calling.